All right, I think we're going here. Let's get it popping. Chapter 6, going with the flow. Feel free to pause the slide here. But essentially what we're going to talk about in this presentation is how does water and how does air affect how we and other objects move when it comes to sports. Now, air and water are what we call fluids. Okay? And fluids exert similar kinds of forces. They all exert some sort of hydrostatic pressure. They exert buoyancy, drag, and lift forces. And we'll talk about these kind of forces here in the coming slides. First, hydrostatic pressure. Hydrostatic pressure is defined as the force that a fluid exerts in order to be able to A, support its own weight, B, support the weight of an object, and C, be able to support the weight of an athlete that is in the fluid. For example here, you've got the pool. Okay? The water in the pool exerts hydrostatic pressure in either to A, support any water above it, number 2, the weight of any object in it, such as these lane lines, and number 3, be able to support the weight of the athlete that is swimming in here. Atmospheric pressure refers to the amount of pressure that the air pushes down on us when we are at sea level. And what we have to think about here is that we've got a bunch of different air molecules above us, essentially like blankets of air above us. And all these blankets of air push down on us because gravity is pulling those air molecules down. Okay? So the amount that air is pushing down on our bodies is equivalent to 14.7 pounds per square inch. And I highlight that right here. Okay, so 14.7 pounds per square inch, that's considered to be 1 atmosphere. So what that's saying is, whatever is the few miles of air above us at sea level, okay, the total amount of air that's pushing down on us is 14.7 pounds per square inch. Okay, so basically every square inch of our body, there's 14.7 pounds of air pressure pushing down on us. Now, it might seem like a lot, but one, because the air is pushing down on a big surface area of your body, it's not as great. Number 2, we just as humans have adapted ourselves. We evolved so that we can handle the forces of air pushing down on us. Now, no matter where we're at in the air that we breathe is typically going to be 21% oxygen, 78% nitrogen, and 1% of any other remaining gases. This ratio of oxygen to nitrogen to other gases will stay the same roughly wherever you're at in the atmosphere. However, how close these molecules together is going to change. For example, at sea level, the air molecules are pretty close together. But the higher up we go away from sea level, such as taking a hike up a mountain, the farther apart these air molecules are. And that's important because the fewer or the farther apart the air molecules are, the less pressure that is exerted on us. And that would make sense. If the molecules are farther apart, that means there are fewer molecules pushing down on us, means that the air is less dense. And this is important in sports because the higher up we play and compete at above sea level, the less oxygen we take in with every breath. This causes us to have to breathe more rapidly because we still need a certain amount of oxygen to be able to help our body or our muscles to contract. Okay? So we need to breathe faster to get the same amount of oxygen molecules in our bodies. Now this, if we have trouble with this breathing and not adapted to it, it can lead to a decrease in performance, and if not properly cared for at high levels of altitudes, this could lead to altitude sickness. Now, we talked about the air pushing down on us. When we get into water, water will also push down on us. Now, water is a lot denser compared to the air. whereas in the air, the molecules are apart from each other. In water, water molecules are right next to each other. So water is a lot more dense than air. And so because of that, the deeper we go into the water, the pressure will increase, but the pressure will increase a lot more compared to the pressure that we feel from the air. Okay? And because there's a lot more pressure on us, okay, if we were to go really deep into the water, there'd be so much pressure of the water around us that our lungs would collapse, we would kind of shrivel up a little bit. In order to help keep our lungs open, we have compressed air tanks, and the compressed air tanks helps balance the air in our lungs with the water forces that are pushing down on us. Okay? And this allows us to be able to dive deeper into the water than what we normally could if it was just ourselves without any other kind of scuba gear. Okay. So to give this into context, whatever it is, I think it's like 5 or 6 miles of air above us at sea level. Okay? That pushes down with 14.7 pounds per square inch. If we just descend 11 yards or 33 feet into the water, that is the same as all of the air pressure on top of us. So the pressure increases by 14.7 pounds per square inch if we just drop 33 feet. Another 33 feet deeper, another 14.7 pounds per square inch are on top of us there. So water, being a lot more dense, okay, pushes down on us a lot more. Now we talked about pressure pushing down on us, but there are also forces pushing up on us. And we refer to the forces that push up on us when we're in any kind of fluid is buoyancy. So buoyancy being that upward force pushing from below us. And this is what causes objects to float in specific fluids. Now we oftentimes think about this in water, us floating, but it also can happen in air. And these buoyancy forces here, it's one of the few forces that helps us go up, help us to fight the effects of gravity. In air, the two examples I like to think about are blimps and hot air balloons when it comes to buoyancy. So one thing to note is if air is hotter, it is less dense. Cooler air is more dense. So the hotter the air is, hotter air is going to sit above cooler air. So in a hot air balloon, if we heat up the air on the inside of the balloon, the cooler air below it is going to be more dense, means that the buoyancy force is going to be pushing up against that hot air balloon. And it's going to help support it and help keep that hot air balloon in the air. Likewise, if we use a different kind of air that is less dense, for example, helium molecules are smaller than the mass of the molecules in our air. So if you fill up a balloon with helium, less dense air is above more dense air, so that helps keep blimps in the air. And the amount of buoyancy force here is kind of determined by Archimedes' principle. Okay? And this buoyancy force, essentially what it is, by Archimedes' principle, it talks about that the force is equal to the weight of the fluid that is displaced by the object. Displacement meaning the amount of fluid that is pushed away due to us or an object sitting in that fluid. The example I like to use is a bathtub. If you fill up a bathtub, water is going to be way high, yay high, maybe like halfway up the tub. But if you get into the water and submerge yourself, that water level is going to rise in the tub. The amount that the water rises in the tub is the amount of water that we displaced based on the size of our bodies. Why this is important is if we weigh more than the water that we displace, that means we will sink. Because the buoyancy force is not large enough to be able to push back up against us. However, if we weigh less than the weight of the water that we displace, that means we will float. We are considered there to be less dense than the water. Now, this often can be explained by different body types. If you're someone who has bigger bones, who has bigger muscles and less fat, okay, you are considered to be denser. If we think back to a couple chapters ago, we saw that picture where you had that large amount of fat and then a smaller amount of muscle that weighed the same. That's because muscle and bones are more dense than fat. So muscle and bones are more dense than fat. So that means they're more likely, muscle and fat are more likely to sink than fat. In fact, never mind, sorry, I apologize. So the more dense you are, okay, the more compressed you are, the more likely you're going to sink. However, if you're less dense, okay, fat being less dense than water, if you have more fat and less bone and muscle, your tendency is going to be to float. The buoyancy force will be enough to help you sit on top of the water. Now, where that buoyancy force pushes the most, that's what we call the center of buoyancy. Okay? And this tends to be higher up in our bodies than the center of gravity. And that's for two factors. Number one, especially in men, we tend to have more upper body mass than lower body mass. Okay, so that's number one. And then number two, lungs have air in it, and air is obviously less dense than the muscle and bone and fat around it. Okay, so because of that, where we're going to be more buoyant is going to be higher up on our bodies compared to our typical center of gravity. And typically, where that buoyancy force is going to act on our bodies is just below our rib cage. We talked before about how the center of gravity is roughly around your belly button, but the center of buoyancy is going to be roughly just below your rib cage. Now, where this comes into play is if you're trying to float in the water, you'll notice here's our center of buoyancy, and here's our center of gravity. There's a small force arm here, and that gravity is pulling down on our center of gravity. And because of that small force arm, that's going to pull our legs down, and chest will tend to lift up a little bit. And it's going to keep doing that there, legs going down and chest up, until our center of gravity lies below our center of buoyancy. And that's typically where you're going to be able to float in the water. Now, that's all well and good if we're just sitting in a fluid, but let's talk about drag. How does drag affect us? And drag affects us whenever we start to move in the water. Essentially what drag is, it's going to be the forces going in the opposite direction that we are trying to go. So for example, we got the swimmer down here. The swimmer is trying to swim over to our right. And as the swimmer is swimming to our right, there are going to be drag forces that are going to be pushing to the left, trying to resist our movement to the right. Now, again, because water is denser than air, we're going to feel the effects of drag more in water, but drag does affect us in air as well. Drag is also dependent on what size we are, the shape we are, and the surface texture that we have. Now we can think about how drag affects us when we move in terms of relative motion. Okay, and relative motion, again, referring to motion of one object compared to the other. So for example here, if I'm running, okay, we are running here, and then we might have like wind or something that's pushing us around, either in front of us or behind us. Okay? So the amount of force that we can push and propelling us to the right here, combined with any other forces that are pushing behind us, such as a tailwind, okay, that might be counteracted by airflow going in the opposite direction. So the more that air flows in the opposite direction of what we're trying to move, And the more that we go into, okay, that air, that's going to create a lot more friction. Okay? So the more headwind we have, and more headwind we're trying to run into, and the faster we're trying to run, that's going to create a lot more friction forces. Versus the slower we move and the less headwind we're going into, we're going to have a lot less friction forces. Now, why is this important? When we get to sports here, okay, we try to maximize friction or minimize friction depending on what kind of outcomes that we want. Okay? One example of this is important are like bike designs. Okay, so bike designs, oftentimes we want to get ourselves moving forward as quickly as possible. In order to do that, we want to minimize the amount of friction from air resistance coming from a headwind that's coming at us. So we want to create bike designs that are very sleek and very lightweight, making it easier for us to go into the wind. We might look at different changes in competitive clothing. Okay, we might want stuff that is more skin tight to help us to be able to cut through the air a lot better, reducing the amount of friction. This might change what we're looking at with relative motion compared with equipment designs. Okay, we want bigger or smaller golf clubs. Okay, we might want certain kinds of helmets, shoes, or cleats to be able to change the amount of friction to help us move the way we want to move. Now, here's an example of how atmospheric pressure changes sports performance. Let's take a look at the Olympics, and specifically the Olympic Games in Mexico City. Now, Mexico City is a city that is very high above the surface, or high above sea level. And because it's high above sea level, that means there's a lot less atmospheric pressure compared to at sea level. And what happened at these games here is Beeman, okay, of the United States, he was able to break the world record in the high jump, and he broke it by 9.9%. That is a huge jump. Okay? If I could decrease my sprint time, 40-meter sprint time by 10%, okay, that'd be like taking off 0.5 seconds, a half a second. That is huge in this world of sprinting. So increasing that vertical jump height, okay, by roughly 2.5 inches, that is a huge increase in performance. Okay? And the reason why this happened is in part due to Mexico City having a lot less air pressure. So he didn't have to push up, or he could be able to fly up a lot higher because he had less force of air pushing down on him. So he's able to jump up a lot higher than if he would have, if the games would have happened at sea level. So where the sporting events occurs at could be how successful the events are could be dictated by the amount of atmospheric pressure. Now, weather conditions can play a role in how much pressure fluids are exerting on us. Okay? We already talked a little bit about air temperature. The warmer the temperature is, the less dense the air is. Okay? And that means resistance of us moving in hotter air is going to be less. So if I wanted to run faster, I would want to run faster, or I would want to run in climates where it is a lot hotter. So I would want to be running in Florida to get a better time versus running in Alaska. In addition, we talked about here how air pressure is higher up, or the higher up we go, the less air pressure there is. So if I want to be moving faster, I want to run at higher altitudes versus lower altitudes. One thing we haven't talked yet about, though, is humidity. Okay, so the higher the humidity, meaning the more water droplets in the air, that actually decreases air pressure. And you might think, why does more water in the air actually decrease air pressure? Water droplets, I should say. And that's because the water droplets are less dense than the normal air molecules. And with more humidity, okay, the water droplets kind of push away the amount of oxygen, nitrogen, and other gas molecules. So humidity, the more humid it is, the less dense the air is going to be. So if I want to run my fastest, I want to run when it's very humid. So another example of this here is if I'm a baseball pitcher, okay, and I want my fastball to be cooking. I want to throw that fastball as fast as I can. I want a warm, humid environment that's done at high altitude. Okay, that's going to produce less drag on the ball when I throw it. Now with a curveball, I want that curveball to be able to spin and change directions a lot easier. Speed is not as important in that with that curveball. So when we're able to do that there, I want more drag, so I want a cooler temperature, I want it to be drier, and I want it to be done at a lower altitude. That will create more drag. Ooh, one thing I wanted to note here and forgot to put in the slide. Remember that humidity is different than actually raining. So if we have actual rain, that's going to be more resistive. That's going to be essentially provide more resistance to us than a humid temperature would be. So if I wanted to run my fastest, I would not want to run in the rain. I would want to run in a humid environment, but not when it's actually rain and water droplets are hitting me. So I mentioned drag, okay, drag, force there. We're also going to bring into this lift, okay. When drag and lift are combined, okay, this produces a resultant force, okay. First, let's define drag again. So drag is the force going in the exact opposite direction that we are trying to move. So again, if I'm trying to move this direction, drag is going to be the force going in the direct opposite way. The definition of lift, though, is the force that's going in a perpendicular direction to drag. So if I'm going straight across, lift would be a force either going up or down at a 90-degree angle. Okay? And the combination of those forces are going to create a resultant force vector, thinking back to a few chapters ago. So, for example here, this is a plane's wing. We're looking at this plane's wing from the side. So we're looking into the tip of the wing, okay? So this plane is going in this direction, okay? It's going to the left. Drag force is going to the right, and lift force, based on how this is angled, which we'll talk about a little bit later, but lift is going to go vertical. This is creating a 90-degree angle, and the combination of the two forces create a resultant force vector, okay, going this direction. And so this is how, if the way this is moving here, this is the direction that this object, this plane's wing, would go based on drag and lift. And what we can do, though, as athletes, is we can manipulate drag and lift to take advantage of these forces. Okay? Now, there are three different drag forces that we're going to talk about. We're going to talk about surface drag, form drag, and wave drag. The first drag we're going to talk about is surface drag. This is also known as viscous drag or skin friction. And essentially, when an object or an athlete moves through a fluid, there's a boundary layer that's created between the object or the athlete. For example, here's a ball up top here, and the movement of the ball through the air creates this boundary layer. Now, there's a certain amount of fluid viscosity, meaning how much does the fluid stick to the specific object, okay? So due to the amount of fluid viscosity, air or the water will cling to that surface and drags at it, okay? And the amount of drag that's caused by this fluid viscosity is kind of dependent on a lot of different things. For example, if I'm biking here, it could be dependent on the surface area of the athlete, maybe the surface area of the bike, how sticky that air is, okay? Is the surface rough or is it smooth, okay? And how fast that cyclist is going. Second kind of drag would be a form drag, okay? And what a form drag means is what is the shape of the object that is moving through the fluid, okay? So depending on the shape determines on how much form drag we experience. Now, let's take a look at this picture on the left here, okay? There are, depending on what the shape is, okay, there is a, it changes how the air flows past the object. For example, up top here, okay, this object here, which kind of tapers off towards the end, air flows very nicely past this object. Versus a ball, a sphere shaped, okay, it doesn't flow very nicely along that shape, okay? The fluid will flow and then it'll kind of come off, creating this turbulent wake behind the object. Okay? And why this is important here is there is going to be a lot of pressure, high pressure, okay, in front of the object. And if there is very turbulence, a lot of turbulence behind the object, that's going to be an area of low pressure, okay? This is considered like the wake. Okay? An object like this, okay, where the air flows smoothly past it, okay, this amount of pressure is not as low as this amount of air pressure. Okay? But why this is important is objects want to go from the area of high pressure to low pressure. So if I've got a lot of high pressure here and a lot of low pressure here, it's almost like the object wants to be sucked back a little bit. So it's going to be a lot harder for a ball to move through the air versus this object. This object right here, high pressure here, relatively high pressure here. A little less than up front, but not nearly as low as this. So this object will be able to move a lot easier through the air compared to this one. So form drag it's very determined by what the object or athlete looks like, okay? How much surface area is being affected by it, and how much high pressure versus low pressure is created by you going through the air. For example here, okay, this bicyclist right here is quite high, okay? There's a lot of surface area that the wind, okay, the airflow going to the right here is hitting, okay? So a lot of pressure in front, high pressure area. It's going to create a lot of turbulence back here. A lot of turbulence means a lot of low pressure. So this athlete is going to have to struggle a lot to keep moving fast. Versus this athlete coming lower down, okay? Now this athlete is in a lot better position, okay? Less of his or her body is being exposed to the air. Therefore, the air is going to flow nice and smoothly over the top, okay, and creating less turbulence in the back, meaning he's going to be able to pedal faster and a lot easier. And then even further, okay, could take it down even more. This is even more aerodynamic. So making yourself more aerodynamic is going to help reduce the amount of form drag because it makes the amount of low pressure in the back a lot less, and or not a lot less, I apologize. Low pressure, there's going to be higher pressure in the back relatively, and this pressure up front is going to be a lot less. So not nearly as much high pressure in the front and not as low of low pressure in the back. Loose fitting clothing, okay, flapping clothing, that creates a lot of form drag. Okay, so that's one reason why in sports like cycling and sports like swimming, we want form-fitting clothing, okay? Because one, it makes the front of the object able to cut through the air a lot easier, okay? It's a smooth surface, so the air running past it, it's not gonna start wobbling, okay? And that turbulent wake in the back is gonna be a lot less, okay? or not going to be a lot less, I apologize. Or yeah, it's going to be a lot less turbulent wake. So therefore, it's going to be a lot higher pressure in the back, meaning that we're going to be able to move a lot quicker. And then thirdly, there's wave drag. Wave drag is a drag that occurs where air and water meets. Okay, you'll see these in a lot of sports that are done on the water. Okay, and how this produces drag is as we're moving through the water, waves are going to pile up towards the front, creating a high pressure wall of water in the front. That's going to resist our movement going forward. You can kind of see it right here. Okay, there's a little bit of a wave up front there. That's going to resist movement through the water a lot more. Okay, so any kind of wave pile up towards the front, okay, that we consider that wave drag. Now, how we can beat wave drag is either tend to be more under the water or to be more above the water. So for example, here's a swimmer here in a streamlined position, staying underneath the water. Now he doesn't have to deal with wave drag. Likewise, Michael Phelps here doing the butterfly, the higher we can get above the water, then we're more in the air versus between the water and the air. So that's going to create a lot less wave drag the higher above the water we get. Now, pools have adapted to account for this to try to minimize the amount of wave drag. A lot of your higher end, nicer pools have specific gutters and lane dividers that are present in the pool that minimizes the amount of waves that are created when we are swimming. Okay, so instead of the water coming, hitting the edge of the pool and coming right back, the gutters allow the water to just seep down, minimizing the amount of waves that are created in the pool. And what this does is, because the water is less turbulent, there are fewer waves, so the athletes are able to cut through the water a lot easier, meaning that times are going to be a lot less, making the pool fast. So we talked a lot about how kind of athletes are moving through fluids, but how does this affect the flight of balls? Okay, as I mentioned before, okay, an object that's more circular instead of tapered off, okay, circular objects can create a lot of turbulence in the back, making a very low pressure area here compared to the high pressure in the front. Very low pressure, which means that ball is kind of getting sucked back there. Okay, a lot of drag due to it being poorly shaped. And this gets worse as velocity increases. So the faster the ball moves, okay, the more turbulence that is created. To account for this, to adapt for this, is golf balls, okay, have dimples in it. Okay? And you might think, shoot, dimples. Okay, why would dimples help a ball fly farther? And the reason this happens is all these dimples creates mini waves that go along its surface. And with these mini waves there, okay, what it does is it minimizes or reduces the amount of turbulent wake in the back. And because there's less turbulent wake, that means there's relatively higher pressure in the back here than it was before. The ball would be smooth. Okay? And if that's the case there, that means the ball can fly farther. Let's talk about lift force. Remember, lift is a force that is directly perpendicular to our propulsive force or our drag force. Okay, and we often see this in terms of an airplane wing. Again, this is looking at an airplane wing from the side. Okay, in order to create lift and get an airplane off the ground, the plane's angle, or the angle for the plane's wings, are going to be tilted up. Okay, roughly up to 15 degrees are considered good for an airplane wing's angle of tilt. Okay, and because of that, this helps create a lift, okay, of that plane's wing as it goes up into the air. And we can take advantage of lift here in a lot of different sports. Okay, for example, in a discus. Okay. Notice here that the discus is going to the right here. Lift force is going up into the air. And why is that happening? Let's think about it in the terms of the areas of higher versus lower pressure. Remember with the previous example, okay, we've got turbulent area right here. Okay, the air is very turbulent. When the air is very turbulent, that means it's a lot less pressure. Okay, versus down here, the flow is moving a lot smoother. So therefore, there's going to be a higher pressure below the disc. So higher pressure here versus low pressure here, it's going to go in the direction of the low pressure. So by throwing it up at an angle, it's going to help to lift the disc higher into the air, which is what we want, because we want to throw that discus as high as possible. Or not as high as possible, we want to throw it as far as possible. So the higher we can get it off the ground, the farther it should be able to go. Now, there might be some times where we want our lift to go down, and we can see this in terms of a spoiler. Okay, so we got a spoiler coming here, and it's coming down at this angle in the back of the car. As the air is flowing here, it's going to flow smoothly over the top, creating a wake at the bottom. So smoothly over the top means higher pressure, okay? And then there's a wake at the bottom, okay? And that helps to keep the car on the ground, because we're always going to want to go in an area of lower pressure. So an area of lower pressure is down here. That's important because we want a lot of traction on the ground when our car is moving. Now, I want to touch on Bernoulli's principle, and it's going to make more sense in one of our last slides. What Bernoulli's principle states is the faster a fluid is moving, the less pressure it produces. Okay, and that's weird, but hear me out here, and we'll explain more in the next couple slides. So the faster a fluid moves, the less pressure it exerts, and the opposite is that the slower it moves, that means that more pressure is going to be exerted. And we can see this in terms of the Magnus effect. Okay, and so what the Magnus effect is looking at a spinning object moving into a specific airflow. So for example, we got a ball going to the left, okay, and it's got a top spin on it, so it's spinning counterclockwise. Okay, so when this is happening here, the flow of the air going past the ball, it's going with the direction of the spin at the bottom, but then at the top it's going against the spin at the top of the ball. Okay, and so what happens there is it's slower velocity up here, which means there's higher pressure there. And what I like to think about it as, the molecules aren't whipping past. Like down here, the molecules are here, and then boom, they go. The air molecules, boom, they go. They're constantly going past it. Versus up here, they're kind of bunching up. They're just kind of chilling here. So there's a lot more molecules up here versus down here. So higher pressure versus lower pressure, this is going to cause the ball to drop. And this might be beneficial. For example, in baseball, if I want the ball to drop down quickly so the batter can't hit it, okay, I want to create a top spin, okay, come in this direction here. So meaning it's going to be slower moving at top, higher pressure, faster moving at the bottom. So that would mean want the ball to drop really quickly. If I wanted to hang in the air, such as hit a deep fly ball, I want the opposite direction. So I want it to spin clockwise. Okay. If I spin it clockwise, the higher pressure zone will be at the bottom, lower pressure at the top, and that would cause the ball to rise a little bit. So that Magnus effect essentially is a spinning object, and how does that spin of the object create a higher versus a lower pressure zone on that object? And how does that affect where the ball moves? Again, feel free to pause here, take a look at those lesson objectives. That's all I got. You got questions, let me know. Peace out, and have a great day. Woo!